Section 1.3, Exponential Functions. Exponential growth. Table 1.6 shows the growth of $100 invested in 1996 at an annual interest rate of 5.5%. Annual interest rate means that interest is compounded annually, once a year. After the first year, the value of the account is always 1.055 times its value in the previous year. After n years, as in any number of years, the value will be calculated by this formula. Y equals 100 times 1.055 raised to the nth power. Remember that n is the number of years that you're interested in. Compound interest provides an example of exponential growth, and it's modeled by a function of this form. In this formula, P is the initial investment, and A is equal to 1 plus the interest rate expressed as a decimal. The equation y equals P times A to the x power, where A is a positive number that doesn't equal 1, identifies a family of functions called exponential functions. Notice that the ratio of consecutive amounts in table 1.6 is always the same. That means if we divide the next y value by the last, we always get the same amount. It always equals 1.005. This fact is an important feature of the exponential curve that has a widespread application. You should also notice, and I'm going off script here a little bit, that if you're looking at a table and you're not sure if it's exponential or not, one key sign to look for is the fact that the amount that each y value increases is changing. The ratio stays the same, as in if I divide this by the last amount, this by the last amount, this by the last, that stays the same. But the actual amount of increase is not constant. That's why we don't use a linear function. If it was growing by the same amount each time, that's when we would use a linear function. We'll start with a little exploration. Read the instructions in the red box, grab your graphing calculator, and answer the questions on the right of your Edpuzzle screen. Moving on for some definitions, an exponential function follows this form. Let a be a positive real number that is not 1, and then the function f of x equals a to the x power is the exponential function with base of a. Of course, you know that we can add a coefficient out front or a constant at the back. That still remains an exponential. The domain of a function like this is negative infinity to positive infinity, in other words, all real numbers. The range of this particular function is only positive numbers and does not include 0. Think about what the graph looks like. You'll recognize that's because there's an asymptote. Asymptote is a key vocabulary term for this unit. Even though it's not on the screen right now, you should stop and make sure that you know what the definition is. If a is greater than 1, then the graph of the function f looks like the graph of y equals 2 to the x, which is what you just graphed above. If a is a decimal, as in a number between 0 and 1, then the graph looks like the graph of y equals 2 to the negative x. Both of these graphs are in your text. They look like this. Again, this is what the shape looks like if your a value is greater than 1. This is what it looks like if a is less than 1. Let's try a quick graphing example. You're welcome to use your calculator. Example 1. Graph the function y equals 2 times 3 to the x minus 4. State its domain and range. If you're having trouble getting started, think about the fact that in your graphing calculator, you will need to type this in as 2 times parentheses 3 caret x and close parentheses before you subtract 4. What you should get is a function that looks a lot like this. You will want to zoom in until you can see a couple key details. The first is the intercept right here, and the second is the asymptote. Make sure that when you sketch these, it's clear that this side of your function is going to go straight horizontally, and that it's never going to go below this line right here, which turns out to be the line at -4. If you think about it, that -4 asymptote line comes directly from the equation, which had a -4 constant at the back. Okay, here's what the book says. Figure 1.23, you were just looking at it, shows the graph of the function y. It appears that the domain is negative infinity to positive infinity, and the range goes from -4 all the way up to infinity. And that's because 2 times 3 to the x will be greater than 0. for all x. No matter what you plug in, this will be positive, in which case the lowest it can be is the -4. For example 2, you should use your calculator to answer this question. I'll pause and have you answer that. Before I show you the answer, this is just a calculator skill to double check that you know what you're doing. As you might imagine, exponential functions obey the rules for exponents. If a is greater than 0 and b is greater than 0, then the following rules hold for all real numbers x and y. This should be a very simple review. Make sure that you understand each of these rules. They will come up a lot in calculus. In Table 1.6, we observed that the ratios of the amounts in consecutive years were always the same, and that was the interest rate. Population growth can sometimes be modeled with an exponential function, as we see in the table below, and in example 3. Table 1.7 gives the United States population for several recent years. In this table, we've divided the population in 1 year by the population in the previous year, so that divided by that, to get an idea of how the population is growing. These ratios are given in this third column right here. What do you notice? So we're going to ask some questions about this table. And one of the main questions we ask in calculus in general is about predicting things. Given the data that we have, what could we predict? For example, what if we wanted to predict the population in the year 2010? We could use this data to make a prediction. Now, what you're used to so far is creating a linear regression. But if you look at these numbers, the amount of increase is not constant. It's going up by different amounts each time. Close amounts, but different amounts. So we're not going to want to use a linear regression. Instead, we're actually going to use an exponential regression. Let me show you what that looks like. I'm using a TI-83. If you need to translate this to your TI-84, you're welcome to look it up on YouTube, but you should basically be able to use the same buttons. So start by turning your calculator on, and then enter these values into your list. And again, you do that by going to Stat, and then hit Enter for Edit. As you can see, I've already put the values in with one quick adjustment. This is a really common adjustment that makes the windowing much easier. Instead of using 1998, 1999, 2000, I designated 1998 to be year 0. And I can do that as long as I'm consistent about how I talk about the rest of the years. If I think about this as year 0, then 2000 would be year 2, 2003 would be year 5, 2010 would be year 10. And that's just going to make my graph easier to see. It doesn't really mean that you'll get the wrong answer using the values in the table, but try it like mine. I'll give you a second to get caught up, make sure that your lists are set, and then if you would, adjust your window so that you can see a graph similar to mine here. To find the exponential regression, which the book will do manually in just a second, you'll next go back to Stat, and then you'll calculate option 0, and I did that by going up. So I want to go all the way up right here to exponential regression. I'm going to hit Enter, and Enter again. And it's giving me now some instructions. It's saying the regression line, the curve that will fit this data, is going to be an exponential one, like this. And that in the spot of A, we should put 276.329. And in the spot of B, we should put 1.01. This is the equation that we just came up with. And then when you put that, actually ignore the 10 to the -7 that Ms. Schaefer used last year. We're just using the normal values that we had here. Okay, here you go. This is the equation you're going to want to use. And if you put that into y1, you should find a line that goes straight through your graph. Let's take a look. And of course, it does look really linear, but if you zoom out, you will see that this is truly an exponential equation. And it is a pretty good model for our data. So going back to the question at hand, if we wanted to figure out what the prediction would be for 2010, right here, all I would need to do is to calculate. So I'm going to go to my graph, and I'm going to calculate the value when x equals 12. Again, because we started in 1998, 2010 would be 12 years later. Oh, looks like I have an error. So when you get this invalid, you're going to need to adjust your window. To make sure that it includes the value we want. So I'm going to go all the way up to 13. And then let's try that again. And you can see the y value it spits out is 311.374. Let's see what the book thinks. Okay. Based on the third column of table 1.6, we might be willing to conjecture that the population in any year is about 1.01 times the population in the previous year. If we start with the population in 1998, then according to the model, we should just multiply this 12 times by the original amount, and they get 311 million, just like we did. Exponential functions can also model phenomena that produce a decrease over time, not just increase like money or population. And this is the case when we talk about radioactive decay. The half-life of a radioactive substance is the amount of time it takes for half of the substance to change from its original radioactive state to a non-radioactive state by emitting energy in the form of radiation. I would hope that you have seen examples like this in your chemistry class, so let me give you a chance to try example form on your own before I show you the answers. Suppose the half-life of a certain radioactive substance is 20 days, and that there are 5 grams present initially. When will there be only 1 gram of the substance remaining? Here's the solution. Notice that you could have solved this both graphically and using your common sense. Either method is great. Compound interest, investments, population growth, and radioactive decay are all examples of exponential growth and decay. Exponential growth and decay are just another word for these same functions that we've been talking about. Growth is just a more specific way of talking about the ones where a is greater than 1, and decay is where we talk about a as being between 0 and 1. Take a moment and make the connection. Growth looks a particular way on the graph, decay looks differently. Make sure you know which one is which. I just showed you how to use your grapher to find a model for exponential regressions, and so we'll use this tool in example 5. Predicting the US population. Use the population data in table 1.8, I'll show it to you in a second, to estimate the population for the year 2000. Compare the result with the actual 2000 population of approximately 281.4 million. Here's the data that you should be using. Just like before, I recommend using year 1880 as your year 0. And in this case, we can also say that 1890 is year 1, and year 2, and year 3. So we're actually counting it in increments of 10, but you can use increments of 1 in your grapher to do this regression. We'll pause here and then show you the answer. Here's the solution for example 5. As I described, we're using our x values to be decades, and decade 0 is 1880. This is the regression equation that you should have if you did that way. When you solve it graphically, you're looking for decade 12, because that's 120 years after 1880. And reading from the curve, we can find that 308.2 is what you should see on your graph, which is pretty close. It's an overestimate, but pretty close. Example 6, interpreting the annual rate of growth. When you do something like we did in example 5, where we use decades instead of years when we graph it.